So, dear students, I welcome you all in this lecture that is based on the course Fields and Galois Theory, MTH 801, a course that I shall be teaching to 8th semester integrated BSc MSc students. So, the course is based on the study of fields, field extensions, and in the later part of this course, we will study some of the basic Galois theory. So, in the first lecture, I will introduce you to what are fields and what do we mean by field extensions. About fields, you are already familiar from your previous courses of study, but for the sake of revision, let us recall some of the basic things about fields. So let me first of all define what is a field. So the definition of a field so the definition of a field so what is field? A field F is a commutative ring with unity such that the set of non-zero elements of F, that is F minus 0, is a group under the operation of multiplication, under multiplication. Or in other words, you can say that a field is a commutative ring with unity such that every non-zero element has its multiplicative inverse in F. So, among the familiar examples of fields, the well-known examples of fields are Q, the set of all rational numbers, is a field with respect to the operations of addition and multiplication of rational numbers, or the set of real numbers, and C, complex numbers. They all are fields where the operations are the usual operations of addition and multiplication of complex numbers, real numbers, and rational numbers respectively. Moreover, we also know that if P is a prime number, then this ring Z mod PZ is also a field. So the standard notation for this field Z mod PZ is actually, it is denoted by this symbol FP. Okay, so here the operations are actually the addition and multiplication modulo P. And we must also note that these fields, the field of rational numbers, real numbers, and complex numbers, they all are infinite fields, whereas this field Z mod PZ is a finite field because it has finitely many number of elements. So in this example, we can just notice that this field Q is actually a subfield of R. Subfield in the sense that Q is a subset of R and Q is a field when the operations of addition and multiplication of R are restricted to Q. And similarly, R is a subfield of C in the sense that R is a field under the operations of addition and multiplication of C when restricted to R. So the general definition of a subfield would then be so let K be a field a subset F of K is a subfield of K if F itself is a field under the operations of K, under the operations of K restricted to F. Restricted to F. Or alternatively, you can say that F is a subfield of K if F satisfies the following two conditions. Number one, F is a subgroup. So F is a subgroup of the additive group of K. So K plus. F is a subgroup of K plus. And secondly, the non-zero elements of F are also form a subgroup. So F minus 0 is a subgroup of this K minus 0 under the operation of multiplication of this K. Okay, so this is the definition, the formal definition of a subfield. So as we have already noticed above, so examples of subfields are Q is a subfield of R, Q is a subfield of R, R is a subfield of C. So thus you can also say that Q is a subfield of C. So apparently it looks like that these are the only fields Q, R and C, the familiar. But in this course later on we would actually construct many examples of subfields K which properly contain Q and they are properly sitting inside this field, the field of real numbers. Or you can say that we would also construct many examples of the fields say L, which are properly containing Q and sitting inside this field of complex numbers. However, we would also prove that, or it is true that there is no such field K which contains this field R properly and which is contained in the field C of complex numbers. So there is no such field which sits in between the fields, the field R of reals and the field C of complex numbers. So this we would also study later on. Okay, and we will also study the subfields. Later on we will have a separate unit on these finite fields where we would study the subfields of finite fields. What is the type of these fields, and we will also study the extension fields of these fields. these finite fields as well as infinite fields. So this was all about a field and its subfields. Now we come to the notion of the extension field of a field. Okay, so what do we mean by extension of a field? So as you have seen here, in case of these examples, you have seen that this you have seen that this Q is a subfield of R. Okay, so alternatively, in the reverse direction, you can say that R is an extension field of Q. R is a large field, it's a bigger field containing the field Q. So C, this R is a subfield of C. Alternatively, you can say that this C is an extension of R in the sense that it is a larger field containing this smaller field R. So if we formalize this in a formal way, then we can have the definition of extension field of a field. So let me put the definition of an extension field of a field. So what do we mean by extension field of a field? So if K is a field, if K is a field containing a field F, containing a field F, containing a field F, then we say that K is an extension of F. Okay, so what is an extension field of a field? It is a larger field containing the smaller field, the subfield. So K is an extension of this field F if K contains F as a subfield. So denoted by this symbol, denoted by K over F. K is an extension of F. So we should not confuse ourselves, because this symbol is also used to denote the quotient ring of a ring. It does not mean here that so the quotient of K by F, it doesn't mean here. Okay, so it is just to denote that K is an extension of F. Or we also denote this extension field of a field with the help of this diagram. So here F K, so it means that F, this base field F is the base field and K is the extension of F. So the bottom field is the base field and the upper field is the extension field. So this diagram is also used to represent the extension of a field. So obviously, as we have seen in the previous example, so we have Q at the bottom. So R is an extension of Q. The real number field is an extension of the field of rational numbers, and the field of complex numbers is an extension of the field of real numbers. And you can also say that this C is an extension of Q. So if Q is an extension of R is an extension of C, you can also say that Q is an extension of C. Now, we have a remark here. Suppose I have given a field F. So I can always find at least one extension of f in a natural way. So what do I do here? So I take this polynomial ring in the variable x. So this contains f. So f is a subring of f of x. And moreover, we also know that if f is a field, then this fx is an integral domain. So fx is an integral domain. And we know that if we have an integral domain, then we can construct its field of fractions. So the field of fractions of this fx would be what? It would be the fractions of the elements of this fx. So it is actually fx over gx, such that your fx and gx, so this fx and gx, they belong to this fx, and of course this gx is non-zero. So this round bracket fx is a field which is the field of fractions of this integral domain fx. So what we get here is that f is contained in fx is contained in this its field of fractions f round bracket x. So this square bracket x is actually the ring of polynomials in the variable x, whereas this round bracket fx is the field of fractions of this fx. So here we have a field, here we have a field, and in between we have an integral domain, but this f is also contained in fx. So f is a subfield of this fx, so you can say that this fx is an extension field of f. So given any field f, we can naturally construct at least one field which is the extension field of f. What is that field? It is the field of fractions of the quotient, the field of fractions of the integral domain, the ring of polynomials with coefficients in x. There may be many extensions of this field f, but at least there is one natural extension of this field f that we construct in this fashion. Okay. So now in our earlier studies of algebra, given any structure, we were actually interested in finding its substructures. Say for example, we have given a group G. So we have given a group G. What we were interested in finding the subgroups of G. Okay. Say for example, we were interested in finding the normal subgroups of G. Okay. Normal subgroups of G. Or we were if the group is finite, then we were interested in finding the zero subgroups of G. What I want to say here is that for this structure of group, we were interested in finding its substructures. Okay. Similarly, for the case of rings, given a ring, we were actually interested in finding its ideals. We were interested in looking at its subrings, ring homomorphisms. But the study of fields is different from the study of rings, subgroups, and other algebraic structures, in the sense that here, instead of looking at a field and its subfields, substructures, field homomorphism, we are actually interested in finding the extension fields of f, looking at the larger fields containing this field f. So what is the reason behind? So we must note, actually we put this as a question. So what is the question? question is question is question is why we are interested in extension fields. So to answer these questions, first I would motivate you, or I would give an example, and then we would try to answer this question in a general fashion. So you take this field f as the field of real numbers. Say, take f equal to r, the field of real numbers. The field of real numbers. And you consider this simple equation, x square plus 1 equal to 0. Okay, we know that this equation has no solution in R. So this equation has no solution in R. So this equation has no solution in R. Or in other words, you can say that this polynomial fx equal to x square plus 1 belonging in this ring of polynomials with real coefficients has no root in R. Has no root in R. It has no real root. So then a natural question then comes in our mind that does there exist a larger field? There exists a larger field containing R, or you can say that does there exist any extension of R in which fx has a root? In which fx has a root. So the answer, which is simple, you all know, the answer is yes. It is actually in fact this equation which led to the foundation of complex analysis, one of the branches in mathematics. So the answer is yes. Here we are not actually interested in complex analysis. We are actually just interested to see the field in which this polynomial x square plus 1 has a root, and that polynomial is that extension of R. So that extension of R is actually the field of complex number where this polynomial fx equal to x square plus 1 has a root. And what is the root? Root is actually I which is square root of minus 1. So for this polynomial we are able to answer this question. Okay, but this leads to the following question, which is a general question. So what is the general question here? So given any field f, and any polynomial fx in fx, does there exist, if fx has no root in this f, then does there exist an extension an extension K of f containing a solution to the equation fx equal to 0, or alternatively you can say that containing a root of fx, that is containing a root of this polynomial fx. So the whole of the field theory is actually based on this question, the whole of the theory of extensions of fields. So this question actually answers, this question actually give you an answer to the fact that why we are interested in extension fields. We are actually interested in extension fields in larger fields due to the fact that given any polynomial fx with coefficients in that field, there is no guarantee that this polynomial has roots in that field, as we have seen here. This polynomial x square plus 1 belonging to Rx, it has no real root. But we are able to find a bigger field, an extension field C, the field of complex numbers of R, containing a root of this polynomial. So with this example in our hand, we pose this general question. Given any field f and any polynomial fx in fx, does there exist an extension k of f containing a solution to the equation fx equal to 0, or alternatively containing a root of this polynomial fx? In fact, the answer to this question is yes. So the answer is yes. So the answer to this question is yes. So answer is yes. And we would, in order to answer this question, we would actually use some of the previous results that we studied on these polynomial rings. So the first result is, you must know this result. So result 1.1. So what is this result? So this result is, if f is a field, if f is a field, then this polynomial ring with coefficients in fx is a principal ideal domain, and hence it is a unique factorization domain, and so a unique factorization domain. So in short, we write it UFD. Number 1. The second result is result 1.2. The second result is let fx be any polynomial in fx, then the ideal generated by this polynomial, so it would be a principal ideal, because in the first result we have seen that if f is a field, then fx is a PID. So but this result says that the ideal generated by this polynomial fx is a maximal ideal, if and only if this polynomial fx is irreducible over f. irreducible, you know, fx is irreducible means that fx cannot be expressed as a product of two polynomials, two non-constant polynomials of smaller degree. That is, you cannot write this fx as gx hx. Okay, you cannot write this fx as gx hx, where gx and hx, they are polynomials of lower degree, polynomials of smaller degree than this polynomial fx. Of course, non-constant polynomials. So we would use this result. We would also use one more result. In fact, proposition or result, you can say. So if you have a homomorphism phi between two fields f and f dash, be a homomorphism of fields, homomorphism of fields, then either phi is identically 0, phi is identically 0 means that phi sends all the elements of f to the 0 of f dash. So it's a sort of 0 map, or phi is injective. So that the image of f under phi, phi of f is either 0 or phi of f is isomorphic to f dash. Okay, because if phi is 0, then the image would be 0, phi of f is 0. So if phi is injective, then phi would be isomorphic to its image. This phi of f would be isomorphic to its image. So phi of f, no, here we have f would be isomorphic to phi of f. So because phi would be injective, so on its image it would be isomorphic. And the proof of this result is simple. It follows from the fact that kernel of phi is an ideal. We know that kernel of a ring homomorphism in ideal forms an ideal. Kernel of phi is an ideal, and the fields have no ideals. So the only ideals of f are 0 and f itself. So if the ideal, if kernel of phi is f, then f would, this map phi would be identically 0, and in the other case phi would be injective. Okay, so any homomorphism between two fields, it has just two possibilities: either it is identically 0 or it is injective. Okay, so with these machinery of three results in our hands, now we are going to answer the question that we have just posed. This is a well-known theorem in the study of fields, field theory. It is called as fundamental theorem of fields theory, or it is also known as Chronicles'theorem theorem. So what is this theorem? So let me write the statement of this theorem. So statement of theorem: So what is this theorem? So fundamental theorem of fields, or it is also called as Chronicles'theorem theorem. So the statement is, so let F be a field and fx be any polynomial in this ring fx, be a non-constant, be a non-constant polynomial, then there exists an extension field E of f and an element alpha belonging to E such that f of alpha is 0. Okay, it is actually the answer to the question that we have just posed, that given any field f and any polynomial in this fx, there is an extension field E of f containing a root of this polynomial. Okay, so just now we prove this theorem. Proof is simple, straightforward. So we have just stated a result, that this result C. If f is a field, then this polynomial ring fx is a unique factorization domain. And what is a unique factorization domain? Unique factorization domain is actually, the definition of unique factorization domain is that every non-zero non-constant can be uniquely expressed as a product of irreducibles. Okay, so this polynomial fx, since it is non-constant polynomial, so since this fx is UFD, it's a unique factorization domain, so it can be expressed uniquely as a product of irreducibles. So it has an irreducible factor. So since fx is UFD, by the result we have just stated, this polynomial fx has an irreducible factor. Say the irreducible factor of fx is, say, px. Okay, now you consider this ring, consider this quotient ring. So fx, our ideal generated by px, you take this quotient ring. Now see this result 1.2, which says that a polynomial, if you take the ideal generated by a polynomial in this ring, it is maximal if and only if this polynomial fx is irreducible. Now you have this px as an irreducible polynomial, so by this result, So this means since Px is irreducible, so this actually means that the ideal generated by this polynomial Px is a maximal ideal, in this fx. Okay, so once it is a maximal ideal, the quotient, we know by well-known theorem in rings that an ideal, so this is a theorem, M is a maximal ideal, if and only if the quotient ring R by M, where R is a ring in which you are taking this ideal, if and only if R by M is a field. So by this result, since this Px is a maximal ideal, so by this result, this quotient ring E, which is fx modulo ideal generated by this polynomial Px, is a field. So I would actually prove that the required extension E of f, this field f in which this polynomial fx has a root, is nothing but this field. We would prove this now. How? Let us see. So now consider the natural homomorphism, the canonical projection pi from this ring of polynomials with coefficients in f, that is this fx, to this fx, our ideal generated by this polynomial px. So this natural map, so it sends any polynomial fx to this fx modulo this ideal generated by px. So this is a ring homomorphism, this is an onto ring homomorphism. So pi is a ring homomorphism. In fact, it is a homomorphism of fields, because this fx is no, it is not a field, sorry, it's a homomorphism of rings, so it's a ring homomorphism. Now what do we do here? Now we now restrict this polynomial, this homomorphism pi. So let phi is pi restricted to f. So it is from now f to this fx, our ideal generated by px. So this pi is this phi is a restriction of pi. So phi is what? Phi is pi restricted to f. So then phi is a homomorphism of fields. Now it is a homomorphism of fields. Because f is a field here, and this quotient ring fx mod this ideal generated by px, which is E, is also a field. So this is a homomorphism of fields. And this phi is not identically 0. Phi is not identically 0. How? It is not identically 0 because it maps. So what is phi of 1? The identity of f. So how do we define this? Phi is actually what? It is restriction of pi on f. So phi maps any a in f to a plus ideal generated by p of x. So it maps this one, the identity of f, to this coset 1 plus ideal generated by px. And this is not equal to px, ideal generated by px. Why? Because px is a multiple, this is a maximal ideal, so it does not contain 1. Because once it contains 1, it would be whole of ring. So being a maximal ideal, it is a proper ideal. So 1 does not belong to ideal generated by px. So phi of 1 is 1 plus ideal generated by px, which is not ideal generated by px. So therefore this phi is not identically 0. Once it is not identically 0, you see this proposition that we have just seen. So either phi is identically 0 or phi is injective. So we are left only with this option, that phi is injective. Okay. So phi is injective. So this means phi is injective. So once phi is injective, then phi of f must be isomorphic to f. Phi of f must be isomorphic to f. And phi of f is a subfield of E. So let f tilde is phi of f, which is a subfield of E, which is a subfield of E. So being an image of a ring homomorphism, being an image of this field homomorphism, it is a subfield of E. Image of a field under a ring homomorphism, so it must be a subfield here in E. So it's a subfield of E. So in other words, you can say that E is an extension of f tilde. E is an extension of this field f tilde. And so an extension of f. By identifying f with f tilde. By identifying f with f tilde. So what do we do here? Because f tilde is isomorphic to f, so we identify f with f tilde. Since E is an extension of f tilde, so we can say that E is an extension of f. Okay. Now, so we are able to find an extension field of f, that is E. Now, let alpha equals this element x plus ideal generated by px. Of course, this is an element of E. Okay. Suppose this polynomial px is of this form. Suppose px is, say, an xn plus an minus 1 x n minus 1 plus so on plus a1 x plus a0. Now what do we do here? We take this p alpha. We actually plug in this alpha for this variable x in this polynomial. Or in other words, you can say that we are going to evaluate this polynomial px at this alpha. So p alpha would be what? It would be Actually, by taking P alpha, we are actually reducing this polynomial modulo this ideal generated by Px. So P alpha is what? An alpha n plus an minus 1 alpha n minus 1 plus so on plus a1 alpha plus a0 plus ideal generated by Px. Okay. Now note that alpha raised to power j is what? X plus ideal generated by Px raised to power j. And by multiplication of ideals, the multiplication of cosets actually gives you that it is x raised to power j plus Px, ideal generated by Px. For j running from 1 to so on up to n. So now what is then this P alpha? Now P alpha would be going to be, so it is actually what? It is going to be an x raised to power n plus ideal generated by Px plus an minus 1 x n minus 1 plus ideal generated by Px plus so on plus a1x plus a1x plus ideal generated by Px plus a0 plus ideal generated by Px. And again, by applying the addition of cosets, you would get that it is an x raised to power n plus a n minus 1 x raised to power n minus 1 plus so on plus a1x plus a0 plus this ideal generated by Px. Okay. And what is this? This is nothing but this polynomial Px. So you are actually getting Px plus ideal generated by this polynomial Px, which is nothing but ideal generated by Px. And ideal generated by Px is what? Which is 0 in this quotient ring fx over ideal generated by Px, which is actually E. So we are getting that P of alpha is 0. So we are done, because we are able to find an extension E of f and an alpha belonging to E such that P of alpha is 0. And once P of alpha is 0, then f of alpha, because P alpha, this Px is a factor of this, irreducible factor of this f of x. So f of x would be actually what? It would be P of x and some other polynomial, say h of x, in this polynomial, this belonging to this ring f of x. Okay. So f of alpha would be what? It would be P of alpha h of alpha, and P of alpha is 0, so it is 0. So you have given a field f, you are able to find an extension field E of f. We are able to find an extension field E of f and an element alpha belonging to E such that such that P of alpha is 0. F of alpha is 0. F of alpha is 0. So we have actually answered the question that we have posed in the beginning, motivated from this, that this polynomial x square plus 1 belonging to Rx has no real root, but there exists an extension C of R containing a root of this polynomial. So we have answered for a general polynomial. So given any polynomial, fx in fx, fx in this fx,